Hi everybody, and thanks for joining my talk. I am Chafika Benzaid, postdoc researcher at Mosaic Lab, Aalto University. Today I am going to present our recent work on enabling autonomous and robust detection and mitigation of application layer distributed denial of service attacks in an SDN environment. And this is a joint work with Mohammed Boukhalfa and Professor Tarik from the same university. The expected massive number of IoT devices and their increasing vulnerabilities combined with the high bandwidth of 5G and behind networks is opening the door to more sophisticated attacks. And one of these attacks is the application layer distributed denial of service attack, which aims at exhausting the resources of an application server, such as the CPU and the memory resources. The application layer distributed denial of service attacks are characterized by a low usage of network bandwidth, and this makes them complex and hard to detect and mitigate. In the recent years, an extensive work has been engaged to address the application layer distributed denial of service issue. And recently, the trend is toward developing machine learning driven software defined security solutions. This trend is motivated by first, the flexibility introduced by softwareization, and second, by the capacity of machine learning to uncover hidden patterns and deliver faster and accurate decisions. But while focusing on the opportunities of machine learning, its security concerns have been overlooked in the contributions made so far. Unfortunately, machine learning techniques have been proven vulnerable to different attacks, such as poisoning attacks targeting the training phase and evasion attacks targeting the inference phase. The attacks against machine learning techniques aim to fool the machine learning model into taking wrong decisions, and this by introducing small perturbations on the real data. Let's take here the example of evasion attack. Using an evasion attack, an attacker is able to generate adversarial distributed denial of service traffic that will be misclassified by the machine learning model as a normal traffic, which allow the attacker to succeed its attack against the application server. To fill this gap, we developed a framework allowing fully autonomous detection and mitigation of the application layer distributed denial of service attack. And this by leveraging deep learning to build a model for attack detection and using SDN controller for mitigation policy enforcement. A key contribution of our work is also to build a deep learning model which is resilient to adversarial attacks. Specifically, here we focus in this work on evasion attack, and we adopt adversarial training as a defense technique, which consists in training the model on adversarial examples in order to learn how to resist these adversarial attacks. The main component of our framework is the application layer DDoS protection component, which is in charge of detecting the malicious activity and generating the security policy in case an attack is detected. It consists of 4 components that are the network flow collector, the features extractor, the detector, and finally the security policy manager. The network flow collector continuously collects the traffic via port mirroring. So each traffic submitted to the web server will be mirrored to the collector. The collected traffic is then exported to the extractor, which will retrieve the the flow features that are relevant for the detection of application layer distributed denial of service. Those features are sent to the detector, and based on these features, the detector will decide if the network traffic is malicious or normal traffic. In case the traffic is a malicious traffic pattern is identified, the detector generates a security policy that will be processed by the security policy manager. The security policy could be, for instance, a flow blocking policy or flow steering policy, or deploying a new security enablers, and so on. Once received by the security policy manager, the security policy is converted to a configuration command in the case of using SDN controller as security enabler. And this configuration command, when received by the SDN controller, the SDN controller will push the flow rule to the corresponding virtual switch in order to enforce the security or the defined security policy. In this example, for instance, is a security policy for blocking the traffic. Our framework can face two kinds of attackers: a normal attacker with the capability of conducting a normal application layer distributed denial of service attack, and also smart attackers which have the capability to conduct normal application denial of service attacks while evading the detection by the machine learning model. The proposed framework has been implemented and deployed on a testbed composed of 3 virtual machines hosted on the same physical server. One virtual machine is used to simulate the attacker's network with 8 attackers that could be normal attackers or smart attackers, and which are deployed on 8 containers. The attackers are targeting a web server by performing either a high-rate HTTP-based flooding attack using Hulk tool, or low-rate HTTP-based flooding attack using Slowdoris tool. To allow the attackers to generate adversarial distributed denial of service traffic, we implemented the evasion attack FGSM, and this using the Clever Hands library. The second VM here contains the web server, which is the victim of the attack, and the application layer DDoS protection module component we developed. This VM is connected to the attacker VM through OVS, and this by using a VXLAN communication. The OVS are then controlled by an SDN controller hosted by the third virtual machine. We assess the framework's performance in terms of 2 metrics that are the web server's response time and the system load, specifically the load of CPU and memory during the attacks. To show the attack effect, the performance metrics were measured before, during, and after the attack, and this using JMeter, which simulates legitimate client accessing to the web server. The evaluation was conducted through 4 scenarios. In the first scenario, we considered a normal attack without any defense system deployed. This scenario is used as a baseline to assess the effectiveness of the proposed detection model. In the second scenario, we considered a normal application layer DDoS attack while using the original machine learning model, which means without adversarial training. In the third scenario, we considered an adversarial attack while using the original machine learning model for the detection. This scenario aims to show the vulnerability of deep learning model to adversarial attacks. And in the last scenario, we consider adversarial attack while using the robust machine learning model, which was trained to resist adversarial attacks. So now for the performance results, regarding the response time of the web server, in the case of Hulk attack, we noticed that while the original model was able to detect the normal attack, it fails in detecting the adversarial attacks. However, we see here that the robust model was able to detect both adversarial and normal the application layer distributed denial of service attack. The same behavior is also observed when using the slow loris attack. But we mentioned here that we noticed that the slow loris attack has a significant impact on the response time compared to Hulk attack. For the system load, the Hulk attack has a high impact on the CPU usage compared to slow loris. We noticed that slow loris, either in with the slow loris, we noticed that the consumption of the CPU is very negligible during the attack. And for the RAM usage, we noticed that for both attacks, either slow loris or Hulk, we noticed a linear increase in the RAM usage during the attack, and which start decreasing when the gradually decreasing when the attack is stopped. To conclude, in this work, we devised and developed a robust application layer distributed denial of service self-protection framework. The self-protection capability of the framework is enabled by using deep learning and software-defined network technology. And its robustness stems from its ability to resist adversarial attacks. In the near future, we are planning to work on other machine learning techniques, such as reinforcement learning and online learning, in order to learn from data stream, and this in real time, and also to investigate other defenses against adversarial attacks. And thank you for your attention.